Okay, 5.3, part B. So, average mean value of a function. The average mean value of a function is actually the mean value theorem for integrals. There's a mean value theorem for derivatives. We did it already. This is the one for integrals. And they usually just refer to it as the average value. Integrals. Sometimes the net change. Okay, so what this is saying is that the average value of a function can be found by integrating and then multiplying by 1 over b minus a. And 1 over b minus a is just the interval you're subtracting and then multiplying by the integral. And that's why basically the average value is just the integral divided by the interval. Now, what the mean value theorem does is when we find our average value, that average value will get us this number right here. It gets us x. We can work backwards to find this x. Now this x is special in particular because if I plug in this x, or c, the c guaranteed by the mean value theorem, it will get me this perfect height that allows me to express the area underneath the curve as a rectangle. Now that's what we were doing, right? But see, this specific height gets me just the right size rectangle that it is exactly the area underneath the curve. Not an overestimate, not an underestimate. This is the exact area. Because this perfect height is basically compensating for all the blank space. It's compensating for all of this that is outside of the rectangle, and it compensates for all of this that is empty inside of the rectangle, because basically this piece here can go right there and it'll fill in that hole, right? Fill in this hole, and now I have all of my area inside one rectangle. That's what the mean value theorem does. It gets you the c value, the x, that will find you the perfect height of a rectangle that covers all of the area underneath the curve. Okay, so example 1, set up a definite integral to find the average value for each function, then evaluate the integral. All right, so if you remember, average value is 1 over b minus a. This is a, this is b. So 1 over 3 minus 0, and then the limits from 0 to 3, and x squared dx. So I'm going to integrate this and multiply it by 1/3. So 1/3, and then I'll put it in parentheses. X squared becomes x cubed divided by my new exponent, which is 3. And then this is getting evaluated from 0 to 3. So 1/3, don't forget to keep carrying on the 1/3. And actually, in fact, if we want to be nice to ourselves, this right here is 1/3 x cubed. I could pull that out, right? I don't have to write it as x cubed over 3. I could pull it out and not have to worry about it within the integral. Could do that. I'm just going to leave it for now. But you can. You're allowed to. What I'm saying is I could do this. This is 1/9. Right? And then just leave the x cubed and then evaluate that from 0 to 3. You can do that. You can totally do that. Okay, I'll just do both. I'll just do both. So this is with the 1/3 pulled out. And then, so 1/9. And then plug in the 3. And I get 3 times 3 times 3, which is 27. And plug in the 0. And I get 0. So 1/9 times 27. So 27 over 9. And my answer is 3. Okay, I'll just continue. Now what if I didn't pull it out? Right? Let's go in the opposite direction here. So 1/3 stayed. And then I'm going to evaluate x cubed over 3. So plug in the 3. 3 cubed over 3 minus 0 cubed over 3, so 1/3, and then 3 cubed is 27 divided by 3, so that's 9 divided by, or sorry, 9 times 1/3, which is 9 divided by 3, which is 3. Okay, of course I get the same answer. All right, B. We're just finding the average value. We're not finding that x that gets me that perfect height. We're just finding the average value, which is basically that perfect height. Okay, the average value gets me that perfect height that is the perfect rectangle. I know I keep saying perfect, but that's really the point. Okay, so next, from 0 to 3, 4 minus x squared. And then because I'm finding the average value, I have to multiply by 1 over b minus a. So 3 minus 0, so it's 1/3 again. There's a lot of 1/3s. I did not do that on purpose. I just ended up using a lot of equations with 1/3 or 0 to 3 or something that equals 1/3. So yeah. Okay, so 1/3, and then I integrate. So 4 becomes 4x minus x squared becomes x cubed divided by 3. And then this is going to be evaluated from 0 to 3. So 1/3, and then I got to do one at a time. I'm going to subtract them. So let's see. Plug in the 3. So 4 times 3 is 12 minus 3 cubed, which is 27, divided by 3, which is 9. If I did my math correctly. And then plug in the 0. So 4 times 0 is 0, minus 0 cubed divided by 3 is still 0. So then I get 1/3. 12 minus 9 is 3, minus 0. So 1/3 times 3, so it's 1. Okay, so at this height, I get that perfect rectangle. And we can find x by working backwards. Although I don't have to do that for this problem, I'm just going to do it briefly because I decided to skip one of the examples. So 4 minus x squared equals 1 at some point. Okay, this is my perfect height. That gets me my perfect rectangle that gets all of the area that's underneath the curve into one nice little box. Okay, so minus 4 minus 4. Negative x squared equals negative 3. Get rid of the negatives, so I get x squared is just 3. So x is technically plus or minus the square root of 3. And this is my C. That's guaranteed, oh goodness gracious, guaranteed by the mean value theorem. Okay, it guarantees that there is an x. It just doesn't find it for us. We have to use the average value to find the x. Okay, so this is what we're going to do in the next example. They're asking us to find the average value and to find that x that will get us the average value. Now, most of the time, our C needs to be in the interval. My interval is from 0 to 3. So obviously, the negative square root of 3, not going to worky. Okay? Next example, this is what we're doing, is that same thing. However, I decided that it would be a better idea to show you what happens when I do negative 3 to 3. On your paper, you have from 0 to 3. I changed my mind and I want it to be negative 3 to 3. Okay, so 1 over 3 minus a negative 3. Oh yeah, that becomes plusy. And then x cubed dx from negative 3 to 3. Now remember, this is the average value. That perfect height that will get me the exact amount of area underneath the curve. Now if you recall, a cubic, x cubed, looks like this. And so what we're doing is we're finding the y value, really, where this area and this area can be depicted in just one rectangle. Okay, so let me continue on over here. So 1 over 6, and then integrate. X cubed becomes x to the 4th divided by 4. And I'm going to evaluate that from -3 to 3. So 1/6, and I'm going to do all the math. All right, so I'm going to plug in the 3. So 3 to the 4th power, that's 81 divided by 4. Did I do that right? See, 3 times 3 is 9, times 27 is 3, 27 times 3 is 860, and 21, yeah, 81. 81 divided by 4. And plug in the -3, and we get the exact same thing. Because the to the 4th power makes it positive. So it doesn't matter that it's negative. So, let's see, I get 1/6 times 0. Ooh, which is 0. My average value is 0. And the reason my average value is 0, if you look at the picture, there's a reason I drew it, because I want to give you a visual. The reason it's 0 is because this amount of area is the same amount of here. This is 3, and then this is, right here, -3. It's the same exact amount, but this piece is underneath the x-axis. Therefore, it is negative. So this negative area cancels out this positive area. So the average, the exact area, is 0. 0. Okay, find the average value, check. And then it says, and all values of x in the interval for which the function equals its average value. So, my function is x cubed, right? Somewhere x cubed equals 0. I need to find that x. Oh, x is 0. X cubed equals 0. Cube root to both sides. And I get x equals 0. So, basically, at 0, 0, okay, this we got from the average value, the y value basically, and this we got from here. At 0, 0, we have that perfect rectangle, which is non-existent because it's 0. I wanted to point that out because if you ever have a graph like that, any graph that is similar to that, so there's a piece down here and a piece up here, and we're doing from these two places, these is going to cancel out these. So the average value is going to be 0. All right, I'm going to try it. Go ahead. This would be a good time to pause this and do it. Okay, so hopefully you did try it on your own and you got 16. So 4 minus 1, and then 3x squared minus 2x dx, and then 4, oops, come on, erase. 3x squared minus 2x, and then 1 and 4. Okay, so do a little math. Make a little love get down tonight. Okay, so 1 over 3. And then, so 3x squared becomes cubed, and then I divide by my new exponent. Minus 2x, and that becomes squared, and I divide by my new exponent. And all of this is being evaluated from 1 to 4. I've been using a stick, but normally, that's not the one I like using. I like using what looks like a bracket. Both notations are correct, or both notations are very common, but I usually use a bracket. I'm just using a stick for now, and I guess I'll start using brackets eventually, maybe right now. I'll just keep going. Okay, so let's see. 1/3, and then I need to plug in the 4, and I need to plug in the 1. All right, so hopefully you're like, oh my god, 3 divided by 3 is uno, 2 divided by 2 is uno, so we don't need those. So plug in the 4. 4 cubed. What's that? Let's see. 4 times 4 is 16, times 4 is 64. Did I say that right? Times 4. 4 times 4 is 16, times 4 is 64. Oh my god, yes. Brain fart! And then 4 squared is 16. So 64 minus 16. I wrote that really big. 64 minus 16. Alright, next. Plug in the uno. So that's 1 cubed 1 minus 1 squared 1. Alright. 1/3. 64 minus 16 is 48, and then minus 1 minus 1. This is 0, right? So 48 minus 0. So I got 1/3 equals 48. And 1/3 of 48 is 16. So my average value is 16. Now, they did not ask me to find the x where my function equals 16. So I don't have to do that here. This is the one I'm going to skip. Example 4, find the general solution. All right, so general solutions have to do with definite and indefinite integrals. Okay, remember indefinite integrals are the ones that we really don't know what they are. So since we really don't know, we always write plus c. We always have our constant of integration. Okay, so when I'm told to find the general solution, that means I'm actually going to figure out what c is. I'm going to figure out what my c is and write the equation whole, not with a constant of integration. And the way we do that is they give us a particular solution. Or, sorry, we're finding a particular solution that we can use with some initial conditions. Initial condition is basically saying, okay, originally, for our function, when we plugged in x equals 1, we get y equals 0 or the function equals 0. That is our original equation. So they're telling us that when we plug in 1 to our original equation, we get 0. So we need to figure out what c is that will complete our equation. Okay, so let me go ahead and start. So here is the derivative. F prime equals 1 over x squared. If I want to find the original, I hope that it makes sense in your brain that if you have the derivative, you need to go backwards. You need to find the antiderivative. You need to integrate. So what we're going to do is we're going to integrate f prime of x. Okay, this is what we're doing. So we're integrating 1 over x squared, which we're going to rewrite as x to the negative 2 power. Okay, we're integrating the derivative. So we're finding the original equation, which we can just call big F of x, right? F of x. Okay, so integrate. X to the negative 2 power. I'm going to add an exponent. So it becomes x to the negative 1 power. And then I'm going to divide by that new exponent. So divide by negative 1. So I'll put a negative in the front. And then plus c. There's my integral. My indefinite, because I don't definitely know what it is. Now, if I'm telling you that this is f of x, this is the original equation, just with the c, my initial condition helped me figure out what c is because my initial condition tells me x was 1, and when I plugged it in, the equation equals 0. So, my equation equals 0 when I plug in 1 into my x. Okay, now that looks ugly. Negative x to the negative 1 power. Okay, I'm going to rewrite that and I'm going to erase this. I'm going to rewrite it. Negative x to negative 1 power is actually, and I hope you're thinking and saying it out loud, 1 over x. The negative stays, right? Okay, so my initial conditions tell me, the equation was equal to 0 when I plugged in 1. So negative 1 over 1 plus c. So 0 equals negative 1 plus c. Add 1 to both sides. C equals 1. So I have my C. Looky, looky. C equals 1. So now I am going to find the general solution. My equation, f of x, okay, is negative 1 over x plus 1. And that's what initial conditions do. They help you figure out what C is. Okay, example 5. Find the particular solution that satisfies h prime of t equals ht cubed plus 5 with initial condition of h of 1 equals negative 4. Okay, so this time is t, it's not x. So what they're saying is that when I plugged in t equals 1, h of t, my original function, equal to negative 4. That's what this is saying. So I have the, what do you call that? Derivative. I'm going to integrate the derivative in order to find my original equation. But then there's a catch because there's a c, but I got to get rid of that c, and that's when we use our initial conditions. All right, so let's go ahead and do that. So integrate 8t cubed plus 5. And go ahead and lower this. Right there is perfect. Okay, so let's see. 8t cubed, so 8t, but instead of to the third power, it's fourth now, and I'm going to divide by my new exponent. Plus 5, it doesn't have a variable, so this was originally 5t. Okay, remember, you can always you can work it out again. Derive what you have. If you get what you integrated, you're good. If I derive 5t, I should get 5. 8 over 4 is basically 2. If I derive 2t to the fourth power, I should get 8t cubed. Right? Okay. Can't forget the c, mustn't forget the c. So, h of t was, oops, that's supposed to be an exponent. H of t was t to the fourth plus 5t plus c. Now this little dude right here, he's my problem. And that's when the initial conditions kick in. Remember, the initial conditions told me that when I plugged in 1, my function equaled negative 4. So my function equaled negative 4 when I plugged in 1 everywhere that there was a t. So negative 4 equals 1 plus 5 plus c. So the 1 plus the 5, that's 6. Okay, I'll write it out. 6 plus c. Subtract 6 from both sides. And I get c equals negative 10. Oh, wait. Gosh darn it. Looking over it, I totally forgot about that 2. That's what I get. This dude right here, I totally forgot him. My bad. So let's see. So that's 2. So there needs to be a 2 here. So this needs to become 2, because 2 times 1 is 2. So this is a 7. I'm sorry. So subtract, or sorry, yeah, subtract. Subtract 7, and this is 11. Alrighty, my bad. So c is negative 11. So my original function, my h of t, and I'll do it in purple. Purple. My h of t was 2t to the fourth plus 5t, and we no longer have to leave c because we know that c was negative 11 minus 11. And here is my general solution. All right, example 6. Move it up a bit here, or in like level of difficulty. Because looky, looky, this is not the first derivative. This is the second derivative. And I don't have one initial condition, I got two. Okay, for this one here, they're telling me that x is 0 and that my derivative um, equals 8. For this one, they're telling me that f, or no, let me continue doing it in the same order, that x equals 0 and that this function equals 4. And I'm starting with the second derivative. So I'm going to have to do the same thing we did for example 4 and 5, but twice. Dos veces. Okay, so integrate. So I'm integrating my second derivative. So x squared dx. Right, so x becomes, or sorry, x squared becomes x cubed, and then I divide by my new exponent. And then plus c. So this is, okay, so if I derived, or sorry, integrated the second derivative, integrating it gets me the first derivative, right? Integrating is anti-deriving. We were at the second derivative, so if I anti-derive once, we should end up at the first derivative. All right, so my first derivative, here's my little equation. I'm going to use my initial conditions. It told me that the derivative equaled 8 whenever we plugged in 0. So 0 cubed divided by 3 plus c. Oh, look at that. Easy peasy. C is 8. Okay, now I can flat out tell you that f prime of x equaled x cubed over 3 plus 8. Now, I'm supposed to go all the way. I need to find the original function. And the only thing we've done so far is find the derivative, the equation for the derivative. So now I'm going to integrate f prime to get f of x. So integrate x cubed over 3 plus 8 dx. Okay, so this will get me the original function. So x cubed becomes x to the 4th. I'm going to divide by 4, but there's already a number in the denominator, so I'm going to multiply 3 and 4. Plus 8. 8. Okay, so what do I have to derive to get 8? I have to derive 8x. And then plus c. So now, I'll be like, okay, so according to my initial conditions, f of x was 4. And in case you don't know where I'm looking, I'm here now. Right? The blue stuff was with this stuff, and then the red stuff is now for this stuff. Okay, my initial condition told me that the equation equaled 4 whenever we plugged in 0 for x. So 0 plus 0 plus c. Oh, another easy peasy lemon squeezy. C is 4. So that means that f of x was x to the 4th over 12 plus 8x plus my c, which was 4. And here is my solution. All right, one more. Find the particular solution that satisfies, well, you can read. This is a try it. This would be the point that you would stop the recording and try it yourself. Okay. All right, so if I want to find the first derivative, because we're starting with the second, this is the equation I'm going to derive, or integrate, sorry. And I get 2x plus c. According to the initial conditions for my first derivative, I get 5 when I plug in 2. So if this is 4, subtract 4 from both sides, and c equals 1. So my first derivative, my f prime of x, is 2x plus 1. Okay, so now for the original. So I will get my original equation by integrating the first derivative. Okay, so if I integrate it, 2x, well, the x has an exponent of 1, so I'm going to add 1 to it, so that's 2. But then I have to divide by my new exponent. And then 1 becomes x, because if I derive x, I should get 1. So if I'm working backwards, if I integrate 1, I should get x, and then plus c. According to my initial conditions, my function equaled 10 whenever I plugged in 2. And obviously these cancel out, right? So 2 squared plus 2 plus c. So 10 equals 4 plus 2 plus c. So 4 plus 2 is 6. Subtract 6 from both sides. And c is 4. And then that means, let me scoot this down. That means that my original function, f of x, the equation for that was x squared plus x plus 4. And there's my solution. Here's your homework. I want you to do this completely by hand. Please try not to use the calculator. I need you to know how to do this by hand. You can use the calculator to check to see if your answer is right, though. And graphing is not necessary. So no graphs necessary. Okay, you should be able to compute all of this stuff algebraically.